Okay, guys. So yesterday we talked about Newton's first law. Okay, we talked about the idea or concept of inertia. Okay, that is the tendency of an object to continue doing what it is already doing in the absence of any unbalanced or net forces. Okay, so when we finished with that, we started looking at what's going to be kind of your most important or initial tool, okay, for doing Newton's second law problems, and that is the free body diagram. Okay, so a free body diagram is just going to be a box. Okay, so you don't have to be an artist to draw a free body diagram. I can draw free body diagrams, okay, because they're just a box. It doesn't matter what the object is, a bike, a person, a car, a boat, it's a box. Okay, and all we do is we write the mass inside. So in this case here, okay, oh, they don't even give us the mass in this one. They tell us the force of gravity. Okay, so we'll just say that the car is 1,500 kilograms for now. Okay, so we've got that, and then we draw on all of the forces that are acting on the car. Now, in their diagram, they actually draw a car, and they draw a point in the middle, okay, where all the forces originate from. We don't have to be that exact. We just, as long as we understand that we do this from the perspective of the forces are actually acting from the center of the mass. Okay, so the forces that would be acting on the car would be the force of gravity, the normal force, and what happens to these two forces? They cancel each other out, but they're still there, so we still draw them. Okay, and we have a force of, they're actually separating the force of friction, that would be between the tires and the road, and the force of air resistance. Most of the time we combine those into one combined frictional resistance force, but we can draw it this way as well. Okay, so this would be the force of friction, and then this would be the force of air resistance. All right, so obviously then this car is not currently under power. Okay, otherwise there would have to be another force, which would be what? If the engine was running and you were pressing the accelerator. Well, it might cause the car to accelerate, but it would be the power of the engine, or the force of the engine, and that would be a forward-directed force. In this situation, they're saying that it has basically run out of gas or something. It says it's coasting on a level road. Okay, so that means that it's in neutral, basically, okay, and the engine isn't providing any forward force on the car. So the only forces acting are gravity and normal force, which cancel, and these two forces. Right? Now, if you remember, yesterday we talked about this idea of net force, okay? And it can be calculated in two ways. Mass times acceleration, which you can't do because I don't know the mass and I don't know the acceleration, okay? Or the vector sum of all forces. Okay? Can I do the vector sum of all forces? Yes. Okay? Now, because the forces are all collinear, I don't need to draw a vector diagram of this. If I did, the vector diagram would look like this. That would be the force of gravity. That would be the normal force. This would be the force of air resistance. And that would be the force of friction. Okay, so there's obviously then a net force acting which way? Negatively, backwards, okay, in a negative direction, something like that. Okay, and then obviously I could add those two together if I knew what they were, and I do. It says that F air is 2,500 newtons, okay, and that the force of friction on the tires is 500 newtons. Okay, everybody all right with that? Okay. the last color I used? Okay, sorry, I got distracted.
Do your pens have like two different tips? Because I know like Miss left, like one side had like a finer tip and one side had.
Okay. I think you can set this to always be the eraser. I haven't figured that out. Okay, so is everybody okay with how that works? Okay, so this would be, the free body diagram will be like our givens, and then we'll go to a vector diagram if necessary. In this case it really wasn't, but we did it anyway, okay, to get our vector sum of all forces. Okay? All right, so we've got the driver in example 1 sees a pedestrian and steps on the brakes. The force of air resistance is 2,500 newtons backwards. With the brakes engaged, the force of friction on the car is 5,000 newtons backwards. Okay, draw a free body diagram of that situation. Okay, well that would be pretty straightforward. We would have the car, okay, even though they didn't tell us the mass, we're just going to say it's 1,500 kilograms, and we would have actually that was the force of air resistance. Okay, and then this. Okay, and we would draw it like that. Okay, we just put our forces on there. Pretty straightforward. Everyone all right with that idea? Okay. Oh, it's just another free body diagram. Okay, we'll get to that. Okay, I want you to try 1 and 2 here. Okay, it's just free body diagrams. Okay, but I'd like you to and calculate the net force. So it's a free body diagram and calculate the net force. Okay, in those situations. So I'll give you a few minutes on those, and then we'll walk through them together. So for question number 1 here, so we got 2 dogs, A and B, are pulling a sled across a horizontal snowy surface. Okay, dog A exerts a force of 200 newtons forward, and dog B a force of 150 newtons. So both of these questions do something very bad. And that thing that's very bad is they don't tell us the mass of the object that's being pulled or pushed. Okay, and they really should do that. All right, so for our first one here, okay, we'll have the box, okay, which is going to represent the sled. We don't know what the mass is, so I'm just going to write M in the middle because I don't know what it is. Okay, dog A exerts 200 newtons forward. Okay, dog B 150 newtons forward. And I do try and represent scale as best I can on my free body diagram. It's not terribly important, but I still try to do it. The force of friction is 60 newtons backwards. And the driver attempts to slow the sled by pulling on it with a force of 100 newtons backwards. Okay, so there's my free body diagram. I have 350 newtons forward, okay? Minus 100 is 250, minus another 60 is 190 newtons forward would be our F net. Okay, everybody all right with that? Okay, so all I did was recognize all those forces are collinear, forwards positive, backwards negative, okay, and go from there. Okay, has anyone ever seen a tractor pull? Okay, so it's you hook up a tractor, a very modified, powerful tractor, to this sled with a weight on it that moves forwards as the tractor pulls it. So it makes it harder and harder for the tractor to pull the sled as the weight moves up and puts more weight on the back, directly on the back of the tractor. Okay, it's very loud and it's fun. Okay, so in the tractor pull, 4 tractors are connected by strong chains to a heavy load. The load is initially at rest. Tractors A and B pull with forces of 5,000 newtons east and 4,000 newtons east. So everything is east and west. Okay, so we'll draw that down here. Okay, we don't know what the mass of the trailer is, so again, we're just gonna write mass in the middle. Okay, we're gonna have 5,000 newtons east, 4,000 newtons east. Okay, and C and D. And 3,500 newtons. All right, so there's my free body. Oh, and then we've got friction exerted by the ground on the load to be 1,000. Okay, so here's the trick to this. Which way should I draw friction? What does friction always do? Opposes. Yeah, it always opposes. So if I've got more force east, the box is moving east, which means friction is acting west. And that's something we have to recognize about the force of friction, is it's always working against you. Okay? So whatever direction this thing is going to end up going, which is clearly east, okay, friction has to act the other way, so I've got to put another 1,000 newtons here. Okay, so I've got 8,000, 9,000 newtons. And what is this trailer not doing? Right. This trailer is not moving because the net force is 0. Or it could also be moving forward at a constant velocity. Right. Remember, those are the two things that can happen when the net force is 0. There's no acceleration when the net force is 0. That is always true. But that could mean it's either stationary or moving at a constant velocity. In this case, it's likely moving at a constant velocity east. Yes. Okay. So for part B, it says, if the load is initially at rest, will it start moving?
Question, sorry, I'll wait to get finished.
No, it's okay. Go ahead.
First question, you have it's 250 in total moving forward and 160 moving backward. Why wouldn't it be 90?
You have
It's 350.
Oh, my bad. Okay,
Okay.
that makes sense.
Yeah, okay. So if the load's initially at rest, will it start moving? No. If it's initially at rest and there's no net force, there's no acceleration. So this thing sits still in this situation. Does that make sense to everybody? Okay. As long as that vector sum, that F net is 0, there's no acceleration. Since we're told it starts at rest, it's going to stay at rest. Okay. There's nothing to get it going. Okay. All right, what if we had one like this, where we had vectors in it? So they've drawn the free body diagram there, okay? One person is pulling 20 degrees this direction, one person's pulling 20 degrees this direction, okay? Obviously the canoe is going to go forwards, okay? But how do I get the vector sum of all forces here? Okay, let's just say that they're both pulling equally, okay? And it doesn't say, or sorry, it does say, yeah, it does say that they are equal. 60 newtons, 60 newtons. Okay, so this is 60, and this is 60. Okay, which way is the boat going to go? Straight forward. Why? Yeah, the angles are equal. So each one of these forces has a horizontal component, and those horizontal components are both directed forwards. They also have a vertical component, and those are opposite, but they're also balanced. They're equal, exactly. So they cancel each other out. So if I'm doing the vector sum of all forces, okay, I've got to break this down into its x and y components, add the x's, add the y's, get my, I mean, I wouldn't actually have to go through that step here because I could recognize they would cancel each other out, okay? But that's something I would have to look at. If I have an angled force, I've got to do what we learned how to do in the first unit, which is find x, find y, get our x's and y's together, and get our resultant. In this case, in this unit, our resultant is going to be our net force, because it will be the vector sum of all the forces. It won't be displacement or average velocity or something like that, like it was in the first unit. Okay? Everybody all right with that idea? Okay, then we got to move on to what is going to be half of this unit. Okay, Newton's second law is half of unit 2. Now, that's going to seem weird because Newton's second law is right here. We're going to spend half the unit on a 3-variable formula? Yeah, it's never that simple. Okay? Because remember, I also wrote just a few minutes ago that net force is actually calculated in 2 ways. Yes, it's mass times acceleration, but it's also, right, the vector sum of all forces. And that's where things can get tricky. Okay? You can have a lot of vectored forces, okay, and things like that that we have to be aware of and mindful of, okay, when we are solving a problem or analyzing a situation. Okay? So, for Newton's second law applies to all situations where F net is not 0. Okay? So F net is not 0, so the object is going to be accelerating in some way in these problems. Okay? So, what's the relationship between force, mass, and acceleration? Well, according to this formula, okay, if I want to increase my F net, okay, I either have to increase this or increase this. Agreed?
Yes.
Yeah, one or the other, or both. Okay? Or I have to add forces according to the vector sum of all forces. Right? If I manipulate this to this instead, okay, it tells me that the acceleration is directly or linearly related to net force. So the greater the force, the greater the acceleration. But it also tells me that acceleration is inversely related to mass. So if I push on an empty wheelbarrow and a wheelbarrow full of bricks with the same amount of force, which one will accelerate more? So I have 2 wheelbarrows. I stand behind the empty one and I give it a push. Okay? Then I stand behind the loaded one and I give it a push. Which one's going to accelerate faster? The one with no bricks in it, because it has less mass, right? So it's inversely related. If I increase m, a goes down because I'm dividing by a bigger number. Okay? This is why, like as a kind of common sense example, sports cars are generally quite small and light. Okay? That's what makes them accelerate faster. There's less mass to accelerate. Okay? I mean, perfect example, they put the same engine in the F-150, my truck, as they do in the Mustang, which is a small sports car. It's the same motor. Okay? The Mustang's faster because my truck is heavier. Okay? Sure, it's just, everything else is the same except for mass. I mean, it's not really, but we'll say it is. Okay? Exactly the same. And so, as a result, the heavier vehicle doesn't accelerate as quickly as the lighter one. Okay? All right. So, that covers all of those things. Okay, so Newton's second law deals with what happens when there's a net force acting on the object. So F net is not 0 in these situations. Okay, so we'll go back to our hockey puck example. When a player strikes a stationary puck, he causes the velocity of the puck to change. That is, it will accelerate. Okay, the cause of that acceleration is the force applied by the stick. So if I've got somebody who's like winding up for a big one-timer, okay, how long is the puck accelerating for? You're right, it would be a short period of time, but let's break that down to, okay, so the puck is, you know, sitting on the ice and he's getting ready to hit it. It's only going to accelerate while Well, the stick is exerting a force on it, exactly. Okay, so once the stick starts to push it, then it's going to accelerate. Once it leaves the stick, but it would, in a real world, yeah, start to slow down. Okay, but let's say it's the perfect physical world and there's no friction of any kind. Once it leaves the stick, then it'll travel at whatever its final velocity of the acceleration was forever after that. Okay, that's obviously not what happens in the real world, but okay, in the perfect physical world, that's what would happen. So you can kind of see that here. Okay, does that sort of make sense? Okay, so that's the other thing we have to remember, that acceleration only occurs as long as the force is being applied. Okay, so as long as the force acts, the velocity will increase. The greater the force, the greater the acceleration, and that acceleration is directly proportional to the force. So if I apply twice as much force, the acceleration will increase by a factor of 2. Okay, so they are directly or linearly related. Okay, and they obviously act in the same direction. So whatever direction the net force is in, that is the direction of the acceleration. Okay, it is not possible for something to accelerate in a different direction than the net force is acting. Okay? If there's multiple forces, that's fine. But whatever their vector sum is, that's the direction of the acceleration. Okay? Okay? Now, we talked about this already. Okay, net force is the vector sum of all of those forces. So if we're looking at the puck there, okay, we would have the force applied by the stick and the force of friction acting backwards, resisting. It's still going to accelerate forwards because the force forwards is greater than the force behind. All right, now, this is what we were talking about here before. So let's say I've got this golfer, okay? And in the first situation, he's using his golf club in the proper fashion, okay? He's going to swing as hard as he can and exert his maximum amount of force on the ball, which has a very small mass, okay? There is going to be a resultingly large acceleration. Now, if for some reason he decided to do the same thing, but he's going to wind up and hit this truck instead, okay, it's still the same force because it's the same guy, same club, okay, but now he's hitting a very, very large mass, which would produce a very, very small acceleration. Okay. Now, in the real world, is that truck going anywhere? No. He's not going to accelerate that truck.
I mean, the rear bumper might have a little bend in it.
Well, that counts. That's an acceleration, okay? At least part of the truck moved, right? And if I was standing at the front of the truck with my hand on the front of the truck,
You would feel the vibration.
I would feel the vibration. That means every particle in the truck moved. They didn't move in unison, which means the truck actually rolled or slid or whatever, okay? But they still moved. Now, if that truck was sitting on perfectly frictionless ice, would the truck actually move? Yes, it would. Yeah, it would absolutely move. Okay? It wouldn't, I mean, the amount of time that it would accelerate for would be very small because obviously the club would be destroyed and the force would only act for a half a second or so. But it would accelerate in that time, and then because the ice is frictionless, it would travel at whatever its final velocity of the acceleration was. Okay? Forwards, probably, unless it slices and then it would go off to the side. Okay? All right, does that sort of make sense? So that's just the relationship between force, mass, and acceleration. Bigger mass, smaller acceleration. Bigger force, bigger acceleration. Okay. All right, so when a net force acts on an object, the acceleration that results is directly proportional to the force and inversely proportional to the mass. The direction of the acceleration is the same as that of the force. That is, in a nutshell, Newton's second law. Okay? Mathematically, that's Newton's second law. Okay. And what was the other way we could calculate net force?
Vector sum.
Vector sum of all forces. Okay, that should also be in here.
What does it mean by a vector sum of all forces?
It means take the forces, put them tail to head, do the x and y components like we did in the last year. So find their magnitude and directional sum. All right, now units for force. Okay,
quick question. When you say that like your acceleration and your force is linear, it doesn't mean it's equal, like your force can be different than.
Oh yeah, the force can be a different number. If the force is 200 newtons, acceleration could be any number because it depends on the mass.
Mass, okay.
But if I went to 400 newtons and doubled the force, whatever the acceleration was at 200, it'll double.
Okay.
Yeah. Okay, so when we multiply mass times acceleration, we're multiplying a mass in kilograms by an acceleration in meters per second squared. Okay, so that means our units for force are kilogram meters per second squared. Okay, which is mercifully abbreviated Newton. Okay, the units for force are newtons. I mean, Newton came up with all of this stuff. He ought to have the units for force named after him. Okay, in the same way that Joule did a lot of work with work and energy and conservation of energy, so the units for energy are named after him. Okay, so that's kind of the way it goes. Ooh, what's this? I don't want that. Okay, is that making sense? So it's just important to know, you're never gonna have to write kilogram meters per second squared for anything, but when you start doing other math and dividing force by something else, you have to know what you're going to get, okay? If I divide newtons by mass, well, the kilograms will cancel and I'll be left with meters per second squared. Or if I divide force by acceleration, the meters per second squared will cancel and I'll be left with kilograms. Okay? That kind of thing. That's kind of what you need to know it for. Okay. Questions there? All right. So we talked about free body diagrams already. Okay, a free body diagram is how we will identify the magnitude and direction of all of our involved forces. Okay, they are not drawn like this. Okay, we don't draw the forces as though they act into the center. We draw them as though they act from the center. Okay, so an upward force and a downward force originate in the center of the box. All right, let's do this example. Very simple Newton's second law type of question. Okay? So we got two people pushing a stalled car. We know the mass of the car is 1,850 kilograms. Okay, so I start out by drawing my free body diagram. 1,850 kilograms. All right, the forces involved are the two people, one of whom is pushing with 275 newtons, and one who is pushing with 395 newtons, so one Hercules and one assistant. Okay? And we know that friction is opposing with 560 newtons worth of force. All right, so now I've got my free body diagram. Are all these forces collinear? Yeah. Do I need to draw a vector diagram for these? No, that would be a waste of time. There's no need for that with this question. So, if I want to find the acceleration, okay, that means I'm going to need the net force and the mass. Well, I have the mass. It's 1,850 kilograms. What I don't have is the net force. How do I get it? Add all the vectors together. It's the vector sum of all forces. So I'm going to have 275 plus 395 minus 560. Okay, that comes out to 110 newtons, yeah? So, 4. Okay, can I calculate the acceleration now?
Yes.
Yes. Okay, so now I would just plug into here, 110 newtons. Okay, divided by 1,850 kilograms. Okay, so 110 divided by 1,850. All right, 0.059 or 5.9. Actually, we have 3 significant digits here, so we can go 5.95 times 10 to the minus 2. Okay, is that a very big acceleration? It's not. But as long as you keep pushing, the velocity of the car is going to increase by just under 6 centimeters per second every second for as long as you push. You're going to have to push for a very long time because that's not very much, okay? But it's still going to accelerate. Okay, has anyone ever had to push a stealth car? Yeah, I had to push one like 2 weeks ago out here. We were leaving somebody's car on that gas. So it happens. It happens. Okay. Back in the day, this is how you started a car if the battery was dead. Okay. If you have a standard, you can start it on a compression, right? Which just means you get a couple of people, you push the car, you get it rolling, and then you jump in, pop it in second, and pop the clutch, and it'll start. Okay. Without having to use the battery, and which was pretty slick if you were that guy that always left his headlights on. It wasn't me.
Sure.
Ever. It's so convenient now that cars turn them off automatically. Okay. Making sense? All right. So that's about as easy as a Newton's second law question gets, because all the forces were collinear. We went directly into F equals m times a, all of that stuff. In basically every Newton's second law problem that you do, you are going to have to use both of these methods. You're going to have to do the vector sum of all forces and F equals m times a. And it's not always going to be in this order. Sometimes you'll have to figure out what the net force is and then work backwards to find a missing force. Okay? This question could have just as easily said, the final acceleration of the car is this, and the pushing forces are this and this, calculate the force that opposes. Okay? And then I would have worked backwards. I would have done this, I would have gone 5.95 times 10 to the minus 2 times mass, got my acceleration, okay? And then divided, and then figured out what my net force is from there, and then subtracted the forces I knew from the net force to get the opposing force, okay? So a question could do that as well. It doesn't really change anything other than the order, but the steps are always there. They just get rearranged. Okay, so that was just the writing for that one. Okay. See how you guys do with this one. So we got two forces. One of them is angled, okay, and the other is directly along the x-axis. Okay? So see if you can calculate the acceleration of the block. Okay, we know the block's 15 kilograms. Okay? And you're gonna have to do some vector addition here. Okay, you guys can do that, I don't have any problem with that. So I'll give you a few minutes, and then we'll walk through it together. So this is a very typical part B to a question like we just did. So this is still the same block. It's still the 15 kilogram block. Okay? We calculated the acceleration of it, okay, in the last slide to be, the net force to be 40.9 newtons. We calculated the acceleration to be 2.73 meters per second. So I'm just going to carry that over. Meters per second squared, and that would be at, it was 47.8? Yeah, 47.8. Okay, so that's something I carry over from the net force part of the question that I did before. Okay, it says that the block is stationary when the force begins to act. We're looking for the displacement of the block after 8 seconds. Okay, is this something we already know how to do? Yeah, it's just an acceleration problem. But very often, with Newton's second law, because the objects are accelerating, we get acceleration problems involved. Okay, So in this case here, we would simply go d equals vi times t plus 1/2 at squared, okay? And that's gonna be 0, so we're simply gonna have 1/2 times 2.7 times 8 squared. So it was 2.73, so I'll include that. Should I use this number, or should I use the number that ended the previous question? Yeah, I have to use the because this is a separate question, I don't carry over all those decimals. I'm not certain of those. My final answer to part A has 3 significant digits. I use that rounded value for part B. Okay, I never carry over an unrounded value from a part A to a part B in a question. Okay, because they're separate entity. So we'll have our 0.5 times 2.73 times 64, which is 8 squared. Okay, so the displacement of this block is going to be 87.4 meters. No, sorry, we only have 2 significant digits. 87 meters at 47 point, actually it'd be 48. It actually, no, it wouldn't. It would be 47.8 because that calculation is not going to affect my vector. Okay, is it all right that I have that 3 significant digits for my vector, but 2 for my magnitude? Yeah, because the vector was never used in that calculation, thus its accuracy was not affected. The magnitude's accuracy was, because I multiplied by a number that only had 2 significant digits. Okay? It's another one of those incredibly rare situations. Okay. All right. This is about as easy as a Newton's second law question can get. Give it a try. Okay, so just so you know, you'd never get one this easy. Okay? Like, this is ridiculous. Okay? I don't even need a free body diagram for this, because what did they tell me? Yeah, they told me the net force. There's only one force, according to this question, acting on the lacrosse ball. Okay, so I know right off the bat, F net is 3.0 newtons. Okay, and I know it's horizontal, and it's on a 0.15 kilogram ball. Right? I'm just being asked to find acceleration, which is simply F net divided by m. 3.0 divided by 0.15 should be 20?
Yep.
Yeah. 20 meters per second squared forward. Okay, or horizontally. Either one of those would be fine. Okay. Okay, questions on that one? Okay. Yeah, those are beneath you already. Okay, try this one. All right, so we got 2 athletes on a rowing team that are training. The first athlete has a mass of 65 kilograms. The second athlete a mass of 70 kilograms. The canoe is 20 kilograms. Athlete A can exert a rowing force of 400 newtons forward, B 420 newtons forward. Water is resisting with 380 newtons. Find the acceleration of the canoe. Okay, so as Alec pointed out, the trick in this question is people forget to add the masses of the athletes to the mass of the canoe when they do the calculation here. Okay? They're in the canoe, thus they're part of the mass that's being accelerated. Right? So in this situation, when we're drawing our free body diagram, okay, we're going to have 20, we're going to have 85, 155 kilograms worth of mass in total, okay, being accelerated in this question. The rest of it's pretty straightforward. you've got 400 newtons and 420 or 380 newtons. No.
380 is, it's 420.
420 is the other one. And then 380 newtons. Okay, so we got 820 going forward. Okay, minus 380 should give us 540? 440. Okay, F net. Okay, equals 400, okay, plus 420 minus 380, 440 newtons forward. Okay, so we've got that. Now we can calculate the acceleration. It's just going to be F net 440 divided by 155 kilograms. I did that right? Yeah. Okay. 2.8 meters per second squared. Okay, everybody all right with that? Fairly straightforward one?
Wait, wouldn't it be 2.84 though, because there's 3 significant digits? Oh, because of the 20, right?
And the 65 as well. And the 70. Okay, any other questions on that one? Okay.
Wait, yes.
Oh, sorry.
I think I got something wrong. Minus 380.
Oh, 380.
No, okay, yeah, I did that wrong.
Got it now? Right, the other two forces are both forward, so we add them.
The net
380.
force is 400, right?
400 and 420, so 2 forward.
Oh, okay, you're right.
Yeah. Okay, now, this question is a good example of a very verbose or wordy question. And oftentimes, you get questions like this that give you information you don't need in an attempt to confuse you. So, read it carefully and give it a try. Okay? It is one of these kind of reading comprehension type of physics questions. Okay, let's draw the free body diagram because that's where the context trick is. In this question, they tell you that in the men's 4-man bobsled event, the maximum mass of a bobsled, 2 riders and a pilot and a brakeman is 630 kilograms. That's nice. It's totally irrelevant. In this question, all 4 of them aren't in the sled. Who's in the sled? The pilot and the brakeman. The other 2 guys are pushing. Okay? I don't know if you've ever watched the bobsled, but all 4 people push to start. The pilot and the brakeman jump in. The other 2 guys, they're like unskilled labor. Okay? They're just, like former sprinters with giant thighs who can push really hard. Okay? Like they just weren't fast enough to make the 100-meter final in the Olympics, so they became bobsledders. Okay? Honestly, most bobsledders are guys that just didn't have the top speed necessary to be great sprinters. Okay? But they're powerful, and that's what you need in the bobsled. Okay? So these last 2 guys are still pushing, while the first 2 guys are already in the sled. So when I'm calculating my mass, I take the 225 plus 98 plus 97. Okay, so I'm looking at 430 kilograms, right? Is it 430?
I think it's 420.
Yeah.
It is 420. Yes, sorry, you're right. See, I shouldn't do math in my head. That's what happens, right? 420 kilograms is being accelerated. Now, the 2 guys who are pushing exert these forces. They exert 1,200 and 1,220 newtons forward. Okay, and the force of friction acting on the sled is 430. All right, and then they all jump in for the ride down the 1,300-meter course. Not needed, not needed. Okay? Those two numbers are completely irrelevant, but thrown in there to see if they can confuse you. Right? So now, this comes down to, I've got 2,420 newtons forward, okay, and I've got 430 newtons backwards, so that should give me 1,990 newtons. Okay, so F net, yeah, I haven't learned my lesson, I'm still doing math in my head when I should. Okay, and that'll be in a forward direction, right?
I did math in my head.
Okay, so that's what I do. And I haven't learned my lesson, I still do it. Okay, so now if I want to calculate the acceleration, it's just going to be my 1,990 newtons divided by the 420 kilograms that's still being accelerated. Okay. Okay, so that bobsled is going to accelerate to two significant digits, 4.7 meters per second squared. And that'll be positive or forward or down the course or something like that. Okay, is that making sense? All right, tomorrow is Thursday. Yeah. Be a super simple quiz, nothing more difficult than these questions that we worked on today. Okay? And we're going to start on to elevator questions and differential acceleration problems. Okay, that sounds really complex, but it's not. Okay? That's what we'll be starting on tomorrow. Elevator.